So, hello everybody, welcome. Buenas tardes a todos. Vamos a empezar. So, today we are going to talk about efficient transformers. I hope the topic is very interesting for you all. So, for the ones that you never came before, this is an event that we organize to try to share and to discuss the last updates, the last new papers and exciting news in the state of the art of artificial intelligence and machine learning. And one topic that is especially important because transformers are everywhere in ChatGPT, in many other places, I think is how can we execute this type of neural networks in our laptops, in our mobile phones, or even in a single GPU, but with a huge power. And for that, we have today a very interesting speaker who is Tomás. Tomás is a researcher in Universidad Rey Juan Carlos here in Madrid, and he was previously one of my most talented students. He just submitted a paper a few months ago about transformers, and I think he will be able to share all his experience in this topic. So thank you very much, Tomás, for giving us the talk, and I hope you guys all enjoy. Thank you.
Okay. Thank you very much, Iago, for presenting me. So as he said, my name is Tomás. I'm right now working at the Universidad Rey Juan Carlos as a computer vision and AI researcher. And the talk from today goes about efficient transformers. So I guess that most of you are probably familiar already with the topic, more or less, with transformers. Maybe you haven't used them as an engineer, you haven't trained them or tested them, but surely you have used them as a user, because transformers nowadays are absolutely everywhere. So they are at the core of today's large language models. They are also used for vision, they are used for diffusion and for many other things. And this great power that they show in many utilities comes with a great cost, in this case in terms of energy, computation, and memory. So throughout the last years there have been many papers, many authors that have tried to make this work in a more efficient way, and that's exactly what we are going to look at today. The presentation won't try to make you experts on any topic in particular. It won't go very deep into any concept, but it will rather give you a broad overview over all the different methods that there are out there right now, and whether to use them or not, and how they work. So first of all, for all of you who are not too familiar with the transformer architecture, I'm going to talk a little bit about attention is all you need. So this paper is from 2017, and it started everything, basically. They presented the transformer as an architecture for modeling language, so for tasks like translation or text generation. Their predecessor was the recurrent neural network, and it had some bottlenecks, some issues, and it was that they had a limited amount of memory. So the memory was stored in a single vectorial representation that had to store the context of the full sequence you were processing. Instead, transformers won't depend on this limited amount of memory, but they will rather allow each token in a sequence look or attend to every single other token in the sequence. So this is what gives them so much power, but also what makes them so costly. So they were first used, as I said, for the language modeling task. But nowadays we have them being used in a really wide, broad range of applications. So we have ChatGPT, Gemini, and Claude as representations, right, of transformers being used for language, but we also have them in vision, the segment anything model, Dino. We also have them with audio, like Whisper or Music Gen. We also have them processing biological data and even used in robotics. And for example, RT2 is a multimodal transformer that is able to process video, language, and even action. So they are a really versatile and powerful tool. Going a little bit inside self-attention, which is one of the main mechanisms that will make this work, for all of you that aren't too familiar with it, This is a way to enrich the vectorial representation of each token in a sequence with contextual information from the whole thing, right? From the full text. So this is just a toy example to give you an overview of how it works. So in this case, we have just 8 tokens, so 8 words forming a small sentence. For each token here, we would compute something called a query and a key. They are just vectorial representations, and the dot product between those will give us some sort of similarity score. So this score will be an indicator of how relevant a word is to another. So if we do a softmax, in this case, column-wise, so for each column, for each query, we can get a score for every other element in the sequence that will tell us how relevant, how important, how related two words are. So for example, the score for blue and creature would be bigger than from blue and forest, because blue is the adjective coming with creature, right? So in the end, each word will get a new vectorial representation, which could be a weighted average of some value vectors computed also from every single token with the sequence, where the weight is this similarity or attention score. So this great power that they have, as I said before, comes with great costs. One of the main issues with transformers is that the complexity of the self-attention mechanism that I just showed before grows quadratically with the input sequence length. So the example before was a toy example. We had only 8 tokens, so that's completely feasible with any small computer, but in reality we will have extremely long sequences. So for example, in the case of ChatGPT, the GPT-5 Pro, we can take up to 400,000 tokens. So as you can guess, the attention matrix could be absolutely huge, and that's not something we can store in memory. That's not something we can play around with ease. And then also during inference with transformers, in contrast to inference with recurrent neural networks, is quite slow. And the reason behind that is that every time we are going to compute a new token, right? So every time we are going to predict a new word, this new token will have to attend to every other token in the sequence that has been generated so far. So as the sequence gets longer, we must store more keys and values in the so-called key value cache, and essentially computation takes more time. And you can actually see this with GPT. If the conversation gets too long, things start to get extremely slow. So this is a short story of efficient transformers, okay? So in 2017, we had attention is all you need. That was the thing that started all of this. And from 2020 onwards, for text generation in particular, we started to process longer and longer sequences. So processing longer and longer sequences led to the need to solve all of these issues, so these bottlenecks that I just mentioned. So we have some papers in 2020, 2022 that will try to somehow approximate attention. So they won't compute the full attention matrix, but rather build some approximation of the attention mechanism. Then we have mixture of experts is another very popular solution. We have some system and compute optimizations that will compute the full attention matrix, but they will optimize the way we compute it algorithmically in the hardware level instead of trying to change the architecture of the original transformer, and many other solutions that we will see shortly. So without further ado, let's start with the first family of solutions. That we're gonna do it that way. And these are the first solutions that try to solve all of these bottlenecks, and they are based on approximating attention. So basically, they will change a little bit the way we compute this attention matrix. They will change a little bit the architecture behind the transformer, try to redefine it in some way to make the computation more efficient. So one of the first ones to try it was Reformer in 2020. So the overall idea, without going too deep into it, is that attention matrices are sparse. So what sparsity means is that when you have a huge attention matrix, so in the case of GPT, it was 400,000 times 400,000, most probably most of the cells, most of the values inside that matrix will be 0. They will be null. So not every token needs to pay attention to every single other token in the sequence. So based on that, they decided to try to find some criteria, some sort of criteria, that could tell them beforehand, so before computing attention, is it worth it to compute attention between these two tokens or not? Where do we need to compute attention in this huge sparse matrix? So they do this via a method called locality sensitive hashing. So basically, they will apply some sort of hash, some function, over every query and every key, and then they will check them in the output space. So after applying the hash, if they are close to each other, so in the same bucket, as they call it, in the output space, then they are supposed to be similar to each other, and then they compute attention. If they end in different buckets, they don't compute attention. So in the end, you will have attention computed only for some pairs, not for all of them. So very similarly, and a little bit later, comes Linformer, but the basis of the idea is quite similar. So they empirically and mathematically prove that the attention matrix is low rank. So if you remember from linear algebra, this would mean that many rows in this matrix are linearly dependent. So basically they are irrelevant, they are redundant, and that leads to the conclusion that we could compress all of this information in a smaller matrix. So upon choosing a constant, so a value k, which is a constant that should be smaller than the sequence length for this to make sense, they will project the values and the keys, the values and the key matrices, through a linear projection that will downsample it. They take the size down, and then they compute attention in a smaller size, right? So the ending product, the attention matrix, won't be n by n. It will be actually n by k. So the complexity is now linear. Complexity now grows linearly with sequence length instead of quadratically. There is another family of solutions that comes a little bit later that will focus on something a little bit different. So they will establish the bottleneck of the attention operation or the attention formulation at the softmax. So the softmax is identified here as the problem. And why? Well, the reason behind this is that the softmax doesn't allow us to use the associative property of matrix multiplication. So basically, applying softmax will force us to compute everything in a certain order. We must compute the full attention matrix, then apply the softmax, and then multiply by the value matrix. So the full attention matrix must be computed at some point, forcefully. However, if we redefine attention, we don't use a softmax, we substitute it by something else, by a different kernel, we could make somehow use of some interesting properties that we will intently look for, and then change the order of the operations. So in particular, they redefine it this way. They define something called a feature map, so just any function over the queries and the keys, and then they will define the similarity between a query and a key by the product of the feature maps. So if we just do this product and don't apply any softmax at all, then we can use the associative property of matrix multiplication and change things and do it the other way around. We can first multiply the keys times the values, then take the query matrix and multiply on the left. So basically, this will allow us to avoid computing the attention matrix by just redefining what the similarity score would be. There are two papers that try to do this in some way. This linear attention paper achieves linear complexity by defining the feature map you can see here, L of x plus 1. The reason why is because it behaves, right? So it has some very good mathematical properties, it is non-negative and so on, so it works. And then we have performer, sorry, that comes a little bit later, and instead of defining any feature map, they will actually try to approximate the softmax somehow. So there is this different solution, okay, that is called grouped query attention and also multi-query attention that will focus on something else. I haven't defined it yet, but usually when we use very big transformers, when we use GPT, we don't use single head attention. So single head attention would be as seen on the left. Okay, so we compute a word embedding, then for this word embedding, we could compute a query, a key, and a value. Instead, multi-head attention is way more expressive, it has way more capacity. It will divide a word embedding into different chunks, and then for each chunk, we compute attention. So we will have a query, a key, and a value for every chunk. So if we have n chunks for each word embedding, we have n queries, keys, and values. So this multiplies by n the amount of parameters, right? It takes the parameter count very high, and it slows things down. But the model is way more powerful. So some papers try to solve this. We have multi-query attention and grouped query attention. For example, this would be the multi-head attention setting, where for each query, for a single word embedding, we compute a key and a value. Multi-query attention decides to group keys along the queries. So we compute several queries, but only one key and one value that is shared across all queries. And then we have grouped query attention, which is basically like a middle point. So we group queries, and for each group, we compute one key and one value. Overall, all of these solutions we have seen so far are approximations of attention. So they change the way the original transformer works and try to make it more efficient. But as you can guess, and maybe you haven't heard of them, it is because they aren't much used. The reason why is because although they are more efficient and they are faster, they lose too much power. So they are not as powerful. These approximations are not very often used. On the other hand, RawFormer is a solution that will focus on a very different plane. Instead of trying to change the way we compute attention, it will change the way we encode position. So this is something we haven't talked about yet. Transformers are agnostic to position. So they will treat a sequence of words just as a bag of words. They don't know which word is the first one, second, third, and so on. They don't have a notion of distance. So we have to inform them somehow. And traditionally, we use solutions like the sinusoidal positional encoding. So all of the traditional solutions will take a word embedding and then add to that word embedding some positional information. And this is a very rigid protocol because it can only encode absolute position. So as the sequence gets longer and longer, this kind of loses expressivity. We don't have a clear and explicit notion of how far two tokens are from each other. We don't have a notion of relative position. So RawFormer, with the rotary position embedding, tries to solve this in a quite elegant way. What they will do instead of adding this sinusoidal positional encoding is they will take the queries and the keys and they will rotate them for a certain degree that will depend on their position in the sequence. So going a little bit into the formulation, but not too deep, don't worry, this is what it does. So for computing a query and a key, we take our learned weights matrix and multiply them by the word embedding. So the rotary positional embedding adds a new matrix multiplication on the left by this very big matrix that you can see here. So what it will do is it will take the word embedding, divide it in groups of 2 coordinates. So it will create a lot of 2-dimensional subspaces, and for every pair of coordinates of 2, it will rotate them. And the reason why it does this in 2 dimensions is mainly because defining a rotation in a 2-dimensional subspace is way easier than in an n-dimensional subspace. You only need the theta angle and that's it, nothing else. So this matrix shows some very good properties that will end up with this. Whenever we compute the product between a query and a key that will give us a notion of similarity, so as an attention score. In the end product, there is an explicit formulation of the rotary, right? The rotary encoding of n-m. So it will somehow directly encode in this product the relative distance between one word and the other. So this is very advantageous, and it really scales greatly with sequence length. In a more visual and less mathematical manner, what they do is they will take each query and each key, as you can see here in the bottom left, divide it in chunks of 2, multiply it by a matrix, and depending on the position they occupy in the sequence, they will be rotated for a certain amount. So this is a very smart and elegant way that will actually allow the transformer to encode position in the queries and learn relative positions. Now, a different family of solutions is mixture of experts. So one of the bottlenecks also that we may see in transformers is that when we try to scale them and make them really, really big, we actually get billions, if not trillions, of parameters. We get massive models. I don't know the exact numbers, but they are absolutely massive. And for each token that we process, we must activate the whole thing, because it is a fully dense, connected network. What the mixture of experts solutions tries to do is, instead of having just one huge network, let's have many smaller networks that we are going to be calling experts. So each of these experts can gain expertise or can specialize in one task or another. So a gating network called the router will be responsible for each token of directing it to one expert or another. So different experts can learn different things, and whenever we process one token, we don't activate the whole network, just part of it. So the good thing is that we can scale greatly a model. We can grow its capacity and its expressivity by taking the parameter count extremely high, but without scaling the cost, because at the inference time we won't activate the whole thing. A very popular solution is DeepSeek MOE, for example, from January 2024, although the first paper that introduced MOE was already from 2017. It is basically the same thing, right? So different papers will offer different ideas, for example, choosing the top K experts, so each token is directed to 2 experts. Other authors will try to double the expert count, making smaller and more specialized experts. And then DeepSeek MOE provides this solution in which we have one static expert, which is like the know-it-all, basically, like the orchestra director, and then other experts will be chosen by the router. So these solutions are actually very promising and very used nowadays. But still we have only talked so far about changes in the architecture of the original transformer, right? So there is another family of solutions we are going to cover now that won't touch the original architecture. So they will respect attention is all you need as it was, right? They will respect the attention computation as it was, and they will focus somewhere else. They will focus on the hardware level. So a very important one was flash attention. So this is from 2022, and it is actually very used nowadays. If you use PyTorch and you build a transformer with PyTorch and you use attention, then this is what's behind. And we also have flash attention v2, which was basically an enhanced version. So let's start with the structure of a GPU memory. So in a GPU memory, we have, as you can see, the HBM. So that's the high bandwidth memory. It is very big, but very slow. And then we have the shared RAM, or the SRAM. This one is way smaller, but it is way faster. That's where computation is done. So the authors here realized that a lot of time when using transformers wasn't spent doing computation. It was actually spent moving things around. So to compute attention, you would have to load the queries and the keys by blocks to the SRAM, then gradually compute the score matrix, write it to the HBM, load it again, compute the softmax, write it, and going basically back and forth. And this is mainly because if you want to compute the softmax, then the most direct way is first compute the matrix and then compute the softmax over it. So you have to compute many intermediate results, many intermediate matrices that will materialize completely in the HBM before getting the actual output. So flash attention basically will solve this issue by redefining the algorithm and computing the attention and computing the softmax incrementally but in one go. So they won't materialize all of these intermediate steps. They won't go back and forth so much. They will just load all the necessary information and incrementally compute the output without having to move so much data around. Then another solution that won't touch the architecture of transformers but will rather focus on the hardware level is FP8, right? So this is a paper that tries it, but the concept is very simple. If you remember when we use floats in a PC, in a laptop, right? In the hardware level, they are represented this way. So you have a sign, which is just one bit, the exponent, and the M and T sign. So you can use different levels of precisions depending on how many bits you use. Usually you will use 32 bits or 16 bits for representing each float number. However, we can use less, right? So for example, well, this is just a number, so you can see how it is displayed. It could be shown using 32-bit precision. We would store this thing in memory, or using 8-bit precision, right? Which is down here. So as you can see, well, 8-bit precision would store 4 times less, right? Would take 4 times less memory than 32-bit precision, and also it would make computation and everything way, way faster. We are using way smaller data and way smaller memory. However, it comes at a cost, of course. So we are losing precision. Actually, this example was handpicked because, as you can see, that number cannot be stored in 8-bit precision. So you are exposing yourself to some rounding and some quantization artifacts that may occur, some numerical instabilities. Up to this day, the concept of using 8-bit precision is mature enough so that we can actually use mixed precision, so storing some things with 8 bits and some with 32 or 16. But it is quite hard to balance, right? Now, so far we have only talked about different solutions for training or doing inference, but many of us are users, or many will be building apps. So SGLang is a framework built on Python that will focus on that part. So it won't help you train or test a transformer, but it will actually help you in the eyes of a user. So when we are building basically an app based on large language models, it will help you optimize its usage. It is, as I said, built on Python, and it comes with many different contributions. This is just a table with some primitives it offers and some of its functionalities. It is very small here, but basically, for example, if you have a multi-call app where you do many calls and you have many branches and many conversations with a language model, it will help you reuse some already computed information. So many branches may have a prefix in common, may have many information in common. It will let you not have to compute all the keys, all the values. Basically, it will avoid duplicating many computations. It also comes with some features that will help you provide structured outputs. For example, if you want a JSON output, well, it can help you force the language model to give you an output that is structured just as you want straight away in a very efficient manner, and it can also help you managing API calls. So it also has some features for optimizing calling APIs, which act like a black box. For example, the OpenAI API. Okay, so these solutions I have shown so far were actually very used nowadays, the ones that try to optimize in the system level. But so far we have only seen transformers, right? So we are going to change a little bit the topic because many may wonder that instead of trying to improve the efficiency over the original transformer architecture and always focusing on transformers, maybe the solution is somewhere else. So if we go a step back and we remember recurrent neural networks, we had this model that was very efficient when doing inference because it could generate sequences in linear time, but it was very slow with training because training was not parallelizable, right? In contrast, transformers are very fast for training because you can parallelize everything, but they are very slow during inference because you have to keep track of the full sequence instead of having one single hidden state representing everything in memory. So maybe there is some way to find some sort of middle ground, something in the middle that will be as efficient as transformers for training and as efficient as recurrent neural networks for inference. So that's the gap that the state space models try to fill in. So a state space is something that goes beyond deep learning. It is basically a mathematical formulation of some sort of dynamical system. So for example, in this we may have some states that can be given just by the xy coordinates of a position, and we may have some actions that will take you from one state to another. So for example, moving left and down or whatever. So a state space model is a way to try to formulate all of this. So basically it will take as an input a sequence, like moving up and left. It will update a hidden state that tries to represent where we are right now, and then it will give you an output, a prediction for the next steps to take, so moving down and right or whatever. However, they were initially defined for dynamical systems that are continuous in nature. So the input sequences will be continuous functions, and so will be the outputs. So that's not how language works, right? That's not directly applicable to our paradigm, to deep learning. So through a process of discretization, we can actually convert this continuous system to a discrete one. So when turning this continuous system to a discrete one, we only have, well, a hidden state, an input, and then we produce an output based on the input and the hidden state. So this looks very much like a recurrent neural network. The main difference between it is that the matrices, the weights we learn, aren't completely free. They are initialized in a certain manner that comes from how we discretize this continuous time dynamical system, and also that it is completely linear, and that's key here. So we don't use any nonlinear activations, it is completely linear, and the fact that it is completely linear allows us to represent the same system in a different manner, in this case in a convolutional representation. So if you know convolutions from image processing, this operation can be easily parallelized, and that's the cool thing. So although we have a bounded context length when we are using convolutions, they are completely parallelizable, so they are very, very good for training. So if you remember, with recurrent neural networks, one of the bottlenecks was that training was very slow. Well, we have built a system, a new type of recurrent neural network that through this linearity approach can be converted into a convolutional representation. So we can take the best of both worlds. We can use the convolutional representation for training that can be parallelized, and then we can use the recurrent formulation for inference, which was already quite efficient, right? However, as you may have seen, the matrices, okay, so the weights that will update the hidden state representation and also the output at each step are always the same. They don't depend on where we are in the sequence. They are always the same. So the problem with this is that they will update the hidden state in the same manner no matter the new input. So for every input, the information of the input that goes into the new hidden state will be of the same magnitude. It doesn't matter how important it is. So Mamba, which is a selective or a selection state space model, provides a solution. So basically it will make the matrices that will update the hidden state depending on the input, and also the matrices that will translate the hidden state to the output dependent on the input. So now the matrices B and C change over time. They are not the same everywhere in the sequence. And so we lose that capability of applying a convolution. So this formulation right here isn't applicable anymore because the matrix B and C are not the same for every element in the sequence. However, they still find a way, okay, to make training very efficient. So they formulate this parallel computation algorithm that won't do everything in parallel, because that is not possible anymore, but it will do everything in parallel in chunks. So for example, they find a way to compute the states H0 and H1 at once, and then H2 and H3 and once. So by dividing it into chunks, for example, of size t, you can get the complexity of n divided by t. So still, it is way more efficient than training a usual recurrent neural network. So in the end, Mamba, what it is, as a conclusion, it is a solution that tries to find some middle ground between transformers and recurrent neural networks. It is very fast when training because it is sort of parallelizable, and it is also extremely fast for inference because it scales linearly with the input sequence length instead of quadratically as transformers did. And also because of the properties these learned matrices have, they are able to store information. So they are able to remember information from the past and not forget about it way better than recurrent neural networks could. So we have seen lots and lots of solutions, so probably your brains are a little bit too packed right now, but we are just going to see one more very quickly, because when the presentation was pretty much complete, suddenly a new paper came out. As you can see, this is from October 2025, but it is too promising not to mention it, at least. So we have this recursive reasoning family. So recursive reasoning will take transformers one step further. Hierarchical recursive model was one of the first papers to propose this. They had some transformers. They actually had two different networks that had, basically different capabilities, and they would process an input, extract an output, and then go recursively. So take the output as an input, and so on and so forth. So basically, they would iteratively build a better and better solutions. So this is biologically inspired by how the brain works or somehow. They are built for reasoning, so for solving problems like Sudokus and stuff. So now, on October 2025, just a few days ago, tiny recursive models appeared. So this is a really, really small model, in contrast with GPT and all of these models that have billions or trillions of parameters. TRM has only 7 million parameters with an M, so it is extremely small. It is based more or less on the hierarchical recursive model, but it takes all of the complexities out. It is extremely simple. It is just a transformer with some extra features that will produce an output, take it as an input, and do a loop iteratively. And they are extremely good. They just beat the state of the art greatly. Yes? Yeah.
Is it the paper that was published by Cornell University together with University of Montreal, sponsored by Samsung?
Yes, sir. Exactly. Yes, exactly that. So if you have read it, you have seen, for example, that on some benchmarks, like I think it was Sudoku Extreme Hard, they took the state of the art, which was scoring a 55%, to an 87% or something like that, I believe. So they beat the state of the art by over 30 points by having only 7 million parameters. So that's extremely efficient, right? Extremely small, something that could fit in any computer, in contrast to the billions and billions of parameters that GPT and all of these models nowadays have. So with all of this information that I had just to speak so quickly in so little time, that's basically the end of this presentation. That's all I had to say. So thank you very much for your attention. And now if you have any questions, of course, I will be glad to answer.
Thank you, Thomas.
Thank you.
Yeah, okay, so questions? Who wants to be the first?
Hi, thank you very much for your presentation. I like it a lot. My question goes about what about all these private companies as OpenAI and Anthropic? Do you think that they are using like maybe a more advanced or efficient architecture that maybe it's not out in research, right? Because they were developed internally. What do you think about it?
I think that's a very good question, and actually that's something I questioned myself also while doing this presentation. When I saw how big GPT is and how big the context window they have is, I wondered, okay, what do they use? And actually what I tried to do to answer that question was ask ChatGPT, and they just refused answering. They said, no, we are a private company, so we can't provide that answer. So personally, of course, I have no idea. I can't imagine what they have, but I guess that they must have been working on something serious, right? Mostly in the computation and system level, probably.
It's for sure not
yes.
quadratic attention.
Yes, it cannot be quadratic attention.
I also would like to thank you for this great presentation, very inspiring. So I'm a big believer of an open source model. I really take all these, Gemini or OpenAI aside, because you never know what actually is the secret source. It might be manipulated.
Yes.
We have no clue. So that's why I'm more into open source. But my question is different. Now, as we see the big race, I would like to ask you, what is the next big thing when it comes to actually development of these models? Because my assumption is that we already exhausted all the data that was available publicly to actually train the models. Now we have all these trends that instead of doing the fine tuning, maybe it's better to go into context engineering, stuff like that. So there are multiple ways, but academia is always ahead of the business. So I would like to know, what is your a strategic beat? What could be the next big thing to focus on?
Thank you very much for your question, and thank you very much for coming too. So I mean that's a very good question. That's tough to answer. In terms of academia, I would guess that, of course, one of the main goals would be, as we have talked here, efficiency. So not exploding so much transformers, of course, not scaling them so much, but doing something a little bit more smart. So instead of going big, going smart and going intelligent. For example, I think maybe Mamba looks very promising, or any of these recursive models for that go iteratively, that they work very smartly. They are very good reasoning models and very compact and lightweight. So I would think that's a very promising direction. But I am just getting into research, so I don't have such a broad view of the aspect. Maybe Iago could add something.
Yeah, I will say that if you read, for example, this paper, the tiny recursive model one, it's learning Sudokus from 1,000 Sudokus. It's impressive. It's nothing in deep learning times, and it's because it's only 7 million parameters. It's a tiny network that you can train overnight, for example. So I think the idea there is to do smarter things, not necessarily bigger things, because you can make it bigger with a bigger data center, but you cannot build another internet, so you don't have many more data. So
sorry, I don't want this to be a discussion, just a question, but what I'm observing, I'm into technology for many years, and now I'm on a commercial side. I'm building banks, but we are using a lot of data, and I also the reason why I'm here, I'm trying to cut the cost because it's killing me. So any idea, more than welcome. But what I can see, though, is that now this big hype of the huge large language model is starting to a little bit like a sunset. So instead, people are trying to go for like a smaller model, very specialized, like for medicine, for aviation, for maybe financial risk management, what have you, and then apply where possible. Because we were so excited that ChatGPT, as you said, forget about the guidelines, but let's say that you can ask whatever question and you can get whatever answer. It doesn't matter whether the answer is correct, but you always get something, right? Because that's how the predictable model works. You can always get something, right? But you know, the smaller model are more specialized, and then you can actually start to even train them as needed, as frequently as possible, and it's going to be so efficient, so specialized, but obviously you cannot ask any question. But you don't need to. If you have your phone, if you want to, you know, put it into the, I don't know, medical machine that is doing the X-ray, whatever, scanning and analysis, you don't need to, you know, learn it to how to speak, you know, Chinese or something, right?
Fully agree. Yeah. Okay.
I had a question that seeing the recent advancements that, as you say, is just 7 million parameters, and that's almost nothing compared with other models. Do you believe that it is even philosophically possible to compress like 20 trillion tokens of training into such a small space of memory? Because the amount of compression you get there would mean that even the human knowledge could be compressed to a huge amount. And do you think that a model, maybe not 7 million parameters, but maybe 8 billion parameters or 1 billion parameters could really be intelligent or have the capabilities of these larger models or even greater?
Well, in terms of capacity, like memory storage, I think there for sure must be like a physical limit, right? So, for example, well, with transformers, that comes directly with the context length. So that's something that comes with the design of it, and that will be the memory it has, right? And then, for example, with recurrent neural networks and all, memory is way limited. So it tends to forget about the past because of the way it is built. I don't think that no matter how smartly you make your design, I don't think it will be able to have this like unlimited storage, right? There must be some sort of physical limit to it. Also, we must also remember that any model you train, it will only be as smart as the data you give it. So it won't be able to reinvent the wheel. It will very dependent on the data you already have available, how you train it. So that's also like a limit for how smart it will be. It wouldn't be able to create something completely new, I don't think, that a human couldn't do. Maybe with more time, but I don't think they could like outdo the best human.
Yeah, but even not doing nothing new, do you think that I could, for example, a model like those with 7 million parameters overfit to a data set of 10 trillion tokens? Like, I don't think now you have, like, for example, ChatGPT could be a trillion parameters, but it is trained on more than 1 trillion tokens. So do you think that the knowledge in the data set could be compressed to a model of such a small size? Like, could you overfit that model to that data set?
Okay. That's interesting. I personally don't think that's possible, right? Like, I don't think so. I mean, what we have empirically seen, at least, is that the more data you have, the bigger the model must be, and also the bigger the model is, the more data you need. So they always come hand to hand. For example, if you have very little data and you build a huge model, things won't go very well. Then when you have a huge model and very little data, I mean, or the other way around, it always goes wrong. So I don't really think so. I think the capacity is completely limited.
Yeah, just for clarity, in this last paper, the one with 7 million parameters was solving specific tasks, like, for example, the puzzle solving and this kind of things. Was not trying to be a chatbot or something that models natural language. Like, obviously you need, I don't know, but billions of parameters or at least a lot of millions of parameters to model language. But, I mean, who cares, right? Because for most of the applications, you don't need to talk with it. Like, you can have an agent that do the chatbotting, but what you are interested in is to solve other problems that many times are just the specific problems, and you don't need such a large language as in human language, right? So
Exactly.
yeah. More questions?
Thank you so much. You have such a skill for mapping the intellectual terrain, and I'm quite envious. And so to take advantage of that skill, I was wondering if you could situate a bit where you would put retrieval augmented generation in this, just because I know RAG is seen as a very helpful solution for solving the inference problem in terms of correcting for the over general training set, and then the context window closing quite quickly, and so you'll have hallucinations. So it's more, I guess, on the memory side, but it does seem to be a kind of response to inference also, and making that more, I guess, reliable, if not efficient, but potentially efficient. So that's why I'm curious about your opinion on that.
Okay, well, thank you very much for for your compliment, first of all. So I'm not too familiar with RAGs. I haven't used them yet, at least. But I would say that they are a bit apart, right? So I don't see them targeting that much efficiency. So I don't think that since you are trying to direct the model in a certain way, you could make use of smaller models. So when you are going to be doing a RAG, I don't think you need GPT for that, right? Because it has a limited context. So in terms of efficiency, the thing is that they are usually directed towards a very, very specific context. So they don't have to know absolutely everything when you are doing a RAG. Really, it is just a tool for helping the model or for allowing it to know a source of information it can retrieve data from and then give it to you. In terms of efficiency, I think the only thing that could come into my mind is precisely that you don't need the model to be that big, right, to capture that information. You wouldn't need a GPT. But I don't know. I don't think it would help in many other ways. Or I can think of them.
Yeah, thank you for the presentation. It was very good.
Thank you.
And I was wondering, maybe you already answered, but what do you think are the most promising research paths, and what do you think are the dead ends towards AGI, let's say?
Well, for the second question, can you repeat that?
No,
please?
I mean the most promising research
Yes.
paths towards AGI, and what do you think are the
Okay.
dead ends?
Okay.
What do you think are not
Yes.
very promising, right?
Yes.
It
So
will turn a dead end, I mean.
definitely, well, from what we have seen, I don't think that scaling and scaling is an option anymore, from my opinion at least, because as we have already mentioned, well, data is limited. So you could keep scaling, but you can't feed it more and more data. The data in this world is completely limited. So I don't think that is really the goal. So we have kind of mentioned, I think how do you say? Well, what we learn from all of this is work smarter, right? Not, well, harder. So I think the future is more related to something a little bit greener, a little bit more optimistic, and not as expensive as ChatGPT. And also solving very specific solutions. So I think the time for such general solutions as GPT, like general language model, these huge foundational models that will do anything from a lot of tasks, I don't think that is the most interesting line of research right now. From what we have seen with, for example, TRM, I think what is more advantageous for researching right now is for specific solutions in a specific domain. So, for example, TRM was great at reasoning, then maybe you can get something that will be great for some specific type of data or whatever. But definitely smaller, smarter models that work for specific domains and tasks. I think that would be it.
Okay, maybe one last question.
So I heard a few days ago about a Spanish startup called Multiverse Computing, and it seems they are doing exactly this, like making transformers more efficient by using tensor networks. So I don't know if you are aware of this thing, or you can make some comment about it.
I am not too familiar about them, to be honest. I
Okay.
didn't know about that company. Do you know about?
I know the company, but I don't know the details of it.
No, not much.
Okay,
Not much.
okay, thanks.
No problem.
Okay, yeah, so thank you very much everybody for your questions. So thank you Tomas also for the presentation. Now we have some catering here, some drinks and snacks, and it's I think perfect moment to chat because I think we have today a incredibly interesting audience, so I encourage you all to go and chat with each other. And yeah, thank you very much for coming, and we are looking forward to see you again in the next event. Thank you very much.